Now, last but not least, all right, my title was Mexican hats and toilets, okay? And so far, I haven't given you toilets. I gave you something close. I gave you the shower, okay? Now I want to talk about toilets, all right? So many systems are poised at the edge of explosion. Trust me, I know that. Okay? A sufficient stimulus takes them across the line. And these are called excitable. And some great examples are toilets, nerve cells, heart cells, grass fires, lots of things like that. So let me explain what constitutes an excitable system. There's a resting state, okay? So you just sit there. There's a threshold. There's recurrent activity. That's the positive explosion. And then there's what's called a refractory period, where it's inexcitable, all right? And you can probably come up with lots of other examples. But the toilet is one of my favorite because you can pretty much map a toilet directly onto a nerve cell, all right? So how am I going to do that? All right. I don't know how much plumbing you guys know, but the way a toilet works is it's got a bent pipe in there, okay, that acts like a siphon. How many of you guys have siphoned gas out of a car? But that was something we did when we were kids. How are you going to set the neighbor's lawn on fire? Okay, now shut up, yeah. And, I'm testing grass fires, right? Okay, anyway, we wouldn't do that. All right, so the idea was when you flush the toilet, it pushes some water up over there, just a little bit of water. That causes a siphon and it pulls all the water out, okay? You can see the same effect if you take a bucket of water and you pour it into your toilet fast enough. If you pour it really slowly, all that will happen is it'll slowly leak out. But if you pour it once, you push it over there and the toilet will spontaneously flush. Okay? So what happens is that's kicking it past threshold. Okay? So if we start with A, here we go. A, boom, we kick past threshold. All right? That causes a great amplification. All the water flushes out. That's the flush. Okay? And then it takes a while for the bowl to fill back up again before you can do it. And that's a refractory period. Neurons have exactly the same behavior. Okay? They have a resting state. Okay? Then, if you give them enough excitation, sodium ions come flying in. Okay? That opens the voltage channels even more, allows more sodium to come in. In the meantime, a delayed potassium current is going outward, okay? That's a positive ion that's going away. It makes you negative and it takes a while to build back up, okay? So toilets are exactly the same as neurons. Neurons are toilets. In fact, I claim you could build a brain out of toilets, okay? And my dream has always been to take a whole line of toilets or a circle of toilets, even better, okay? Take a circle of toilets, block, and have their output go into to their neighbors, okay? Block one toilet off, flush this one. That will cause the wave to only go in this direction. Presumably, by the time it comes back around, if you had enough toilets, this guy would have recovered and filled his bowl enough to start the thing up, and you'd get an infinite oscillation. Okay? So that's my dream. Everybody has to have a dream, and Kohler won't answer my emails. All right. So let me give you some examples of what you can do with an excitable medium in one dimension. All right, so this is a really simple little model for an excitable medium that you can write down, a little mathematical model, okay? Is the dynamics sit on a circle, okay? They have a stable rest state and unstable rest state, okay? So you're on a circle, okay? I guess this is the stable rest state here. Sorry, okay? The red is stable, the green is unstable, okay? So that if I kick it past this green guy, then the dynamics forces me to go all the way around, and then I come back to rest, okay? So if you put a whole bunch of these guys in a line, then it turns out that you can get, this is an example of an experiment with Harmacol waves, and this is the same thing with a little model with some randomness in it, and you can see you get very nice traveling waves that zip along there. Now in 2 dimensions, that's where the fun starts, because in 2 dimensions, then you can start to get really complicated dynamics. Does anybody here ever play this game called it was called Life, okay? It was a cellular automata. We've heard a couple of cellular automata talks here. I really like cellular automata, and I'm surprised that there aren't more iPad cellular automata apps. There should be, because it should be something that somebody easily built, okay? So here, let's imagine a 2D grid, okay? And I'm going to show you what happens in a second, okay? Red is excited, blue is refractory, and empty is rest, all right? And if you're empty and one of your neighbors is red, then you become red on the next time step, okay? And if you're red on a current time step, then you become blue on the next time step. And if you're blue, then you become empty, okay? So you can modify these. These models are called Greenberg-Hastings cellular automata. All right, so here's how you get spirals, all right? Persistent activity. But let me start with just the simple, consider the following simple experiment. Suppose I just excite the guy in the middle and don't do anything else. What happens? On the next step, his 4 neighbors become excited. And then in the next step, those neighbors become excited and those guys become refractory. And all you get is an outward going, like throwing a pebble into a pond. You get an outward going. Now suppose instead that I start with a red line here and a blue line there, okay? Now what's going to happen? All right, well, on the next step, this red guy can come on, but nobody over here can. It's hard to see this, but all these blue guys turned off, and these red guys became blue. That's these guys, okay? And there's one red guy here, so this guy comes on, and then these 4 guys come on. Right? That's this guy and these 4 guys. And these are the 5 guys that were off. I'm sorry, 5 guys. All right? Next step, these 5 guys become blue. These guys are off. This guy comes on, and this guy comes on, and these guys come on. And there's these guys coming on. Okay? And now the next step, starting to curl around. And now you can start to see that this is forming a very nice spiral wave. And it will persist. This will stay forever. Okay? So this is a really simple model. And now my real dream is to arrange a 2D grid of toilets to make a rotating wave. Okay? So basically, here's the same thing. I do the same ring dynamics in a 2-dimensional network. And there I can get double spirals and single spirals. And these are some examples of the rotating spirals I showed you already. Oh. So I think I'm about done here. I don't know how much time good. 7 minutes. Nobody will complain if we go drinking early. Just kidding. I meant Coke. Coca-Cola. Okay. So basically, what I wanted the take-home message I wanted to send to you is many patterns have a great deal of structure. And the simple principles can be applied to all of these. You can understand a lot of stuff with only a few simple principles. And spatially and temporally structured interactions that have this sort of positive, this yin and yang of positive and negative, are enough to give you a whole panoply of really interesting dynamics and patterns. So I think that's it. Thank you.
Any questions?
I think you like our toilets. I want to ask, can we mimic or develop a device?
Can we mimic?
Can we develop a device mimicking, say in the toilet, but in a neuronal activity to activate like neurons, but in a device?
In a what?
In a device.
Oh, a device. Oh, yeah. Yeah, in fact,
One
I have, yeah, people have little artificial neurons that you can make. I have actually, sitting on my desk at home, a device from AT&T Bell Labs that's about this big. It's an artificial neuron, okay? And many years ago, 30 some years ago, I was in Japan and I visited Fitzhugh's lab. And Fitzhugh basically had an array, not Fitzhugh's lab, Nagamo, the Fitzhugh Nagamo. He had, I think, an array of 20 by 20 of these really primitive devices hooked up with little resistors between them that generated rotating waves and things like that. So yeah, people are doing that now. You can put neurons on a chip. People are making big networks on chips. Okay, so now you get into the issue of what can you do with these, and there what really matters is how you hook them up. And this is a really simple story I've told you, because there are actually excitatory neurons and inhibitory neurons, and it really does matter how you hook them up.